Hello everyone, welcome to our discussion of section 8.6 where we will be talking about representing functions as power series. Now the main reason we like to do that is because we can take the derivative of such functions, or integrate such functions, and also be able to approximate such functions by polynomials. So these are some of the few uses of this endeavor. Now for power series, one useful power series that may be used for representing functions is the one that you see on the screen right now. Now given this power series, then the radius of convergence, this series converges when absolute value of x is less than 1. So let's do a few basic examples of this, applying that power series, and then after that we will shift to applying the same method to taking derivatives and taking or integrating functions. So here we want, for example, to find a power series representation for the function that you see here, and determine the interval of convergence. And of course, if we are to determine the interval of convergence, we ought to know the radius of convergence as well. The two go together. Well, first thing, consider the power series that we just saw, right? This one. I'm just going to rewrite it here. With all its individual, a few of its individual terms like that. So this power series is represented by this function we're saying. And this, of course, converges when absolute value of x is less than 1. Okay? So the function that we have can be written in a similar format. In other words, we're going to use this format to rewrite our functions. Our function actually almost, it's similar to this, but of course it has differences. But notice that it has a 1 here, minus, minus. But instead of 1 in the numerator, we have 5. That's no problem. We can factor this out. We can factor the 5 out and we'll get 1 in the numerator. That way we have the numerator, this part and this part the same, and then we will be left with 4x squared rather than x. But you'll see how this similarity between the function and the function that represents this power series becomes so useful in taking the derivative and integrating various functions. So the first thing to do is let's factor this 5 out. And our objective is to get this expression to look like something like this. So we can write f of x equals 5 times 1 over 1 minus 4x squared. Right? So now, instead of the x, everything is the same except the x and 4x squared. These are the different terms. But this is great because now we can rewrite this power series, which represents this one, this function, such that the 5 is going to be a factor in front, and instead of x, which ends up here to power n, we have 4x squared to n power. Okay, so let's make use of that. So we will have then, therefore, this will be equal to 5 times that, and going from 0 to infinity, instead of x, which belongs to this x here, right? This function is representative of this power series and vice versa. So instead of x, we have 4x squared to n power. Okay, so we kept the factor out and in front of the series. So this is what we know, which converges when absolute value of x is less than 1. And by making this expression similar to this, we are modifying the series as well accordingly. So the 5 factor ends up in front. Instead of x, we have 4x squared, and that ends up here raised to power n. Okay, and then of course we can just take the 4n out. We can rewrite this 2 if we like that, and then 4 to n power, and of course x to 2n power, right? So now we also have to, here they're asking us to determine the interval of convergence, and we have to start by noticing what the radius of convergence is. So the radius of convergence for this power series is, of course, r equals 1, right? We learned this in the previous section, 8.5. So for this power series, then the absolute, instead of absolute value of x, we have absolute value of 4x squared should be less than 1. So let's write that down, converging so this power series represents, and let me actually write that here, 5 over 1 minus 4x squared. So this power series represents that function which we started with here, and this power series converges when absolute value of 4x squared is less than 1, right? So of course we need to find the interval of convergence based on this. So let's so that will be simply 4 times absolute value of x squared less than 1. So absolute value of x squared is less than 1 over 4. All right? And then of course x, or absolute value of x is just square root of the other side. So it'll be 1 over 2. So from this, the result is that r, they didn't ask for this, but we can easily see that r is 1, or radius of convergence is 1 over 2. And the interval of convergence, which is what they're asked for, is from negative 1/2 to positive 1/2. In other words, so x varying between, right, from here, we know that x varies between negative 1/2 and 1/2. Therefore, the interval of convergence is parenthesis negative 1/2 comma 1/2. Okay, so this is the interval of convergence, and this is the power series representation of the function that we started with. So these are the two things we needed to find for this example. Okay. Let's do another example. So try this one without looking at the video first. I would, because you've seen this example, first example. So just pause the video and spend 15-20 minutes on this, and then come back here, see hopefully our solutions agree. Okay, so just like the previous example, I'm going to begin with the function that we have and the power series that represents it, which is consider or recall that we have 1 over 1 minus x equals represented by this power series, given that absolute value of x must be less than 1. Okay, so this is condition for convergence. Okay, so now let's see if we can write this function in this form, because then that means we can modify, however we have to modify this to write it in this, similar to this format, we can modify the right-hand side to write this function in terms of a power series, which is our objective. Okay, so the first thing is, first of all, we need a 1 in the numerator. Right now we have x, and we need a 1 there. We have 9, and then of course that has to be minus, it's plus, so there's a whole bunch of things we need to do. So let's rewrite this function as f of x equals, I'm going to factor out x over 9. Okay, so if we factor out x over 9 from what we have, then we will have 1, right? This would have to be 1 times x is going to give us x. Then here we will have, of course, 1, which is what we want. And then instead of minus x, we'll have to have, we need to end up with plus x squared, right? So we will have minus, and then we will have minus here, minus x squared over 9, right? Just factoring 9 from the denominator, we should end up with this. And of course, because we want this to look like that, that's why I had instead of plus, I have minus. Okay, so now we have 1 in the numerator here, 1 in the numerator here, 1 here, 1 here, minus. But instead of x, we have minus x squared over 9, which is fine. So we're going to replace this x in the power series for this function with minus x squared over 9 to n power. Let's not forget, we were able to get this format because we factored out x over 9 from this. So we have to include that in front of the power series. So then, therefore, we have x over 9, and I'm going to write the power series for that function. So x over 9 times n from going, the index of this series going from n equals 0 to infinity. Instead of x, we will put this minus x squared over 9 to n power. Okay, so can we simplify this a little bit? Yes, we can. But right away, we can obtain the radius of convergence right from the get-go, right? This is sufficient for us to determine the radius of convergence. But let's simplify this a little bit. So we have x over 9 in front, and then we have the series notation. Instead of minus to n power, let's pull minus 1 out, because that's the convention usually when we are writing the alternating series. So like that. So minus 1 to n power, that's for this minus. Then for the rest of this, of course, we can write as x over 9, or x squared over 9 to n power. Okay, that's one step simplified from the previous one. Can we distribute the n? Absolutely. We can distribute this power on the outside to each one of the terms here. Let's do that. And so we have x over 9 times x to 2n divided by 9 to n power. Can we simplify this more and make it look more like a conventional way of writing the series? Absolutely. We can distribute this into this, right? We have x times x to 2n power. We'll get x to 2n plus 1 power, right? So let's do that. I'm distributing this x into that. And let me not forget this term. And then so we have x to 2n plus 1, which is the result of distributing this term into that. And of course, 9 can be distributed into that. Instead of 9 to the n, we get 9 to n plus 1 power. Okay, so this is the power series representation of, can I put it on the screen? Well, barely. Let me write it again. So this is the power representation of, or the power series representation of this function. Okay, so we achieved part of what the problem was asking us, which is that. Okay, now we need the radius of convergence. Well, the radius of convergence we can get from here, right? This quantity, remember for our base function and the associated power series, the absolute value of x had to be less than 1 for this series to converge. So for this series to converge, the absolute value of this quantity has to be less than 1. So let's write that down. Converges when absolute value of minus x squared over 9 is less than 1. So of course this minus will get canceled out with the absolute value, so we will end up with absolute value of x squared over 9 less than 1. Let's simplify this a little more. We end up with absolute value of x squared less than 9. And then, of course, so the radius of convergence is 9, which they weren't asking us for this, but this tells us that the interval of convergence is like that. Okay, so we will have, let me write that here, the interval of convergence would be parenthesis -3 to 3. Okay, so we have that. I hope this agrees with the work you did. So hopefully things are making sense at this point. Let's do another example of this type. Again, we want to represent this function in terms of a power series and also find the interval of convergence. So after these two examples, maybe it's a good idea if you pause the video and see what you come up with in your own solution in 15-20 minutes. Okay, so once again, recall that 1 over 1 minus x is a function that is represented by this power series, which converges as absolute value of x is less than 1. Okay. Now let's try to put this in this form. We already have a minus there, that's good, but we do want a 1 in the numerator. That means we need to factor out x squared, and we also need a 1 here to look like that. That means we need to factor out a cubed. Okay, so let us do that. So this function we can write it in factored form as x squared over a cubed times, all we need is a 1 in the numerator. We have to have a 1 here. What about here? What about x? What should we have there as we factor out a cubed? As we factor out a cubed from this denominator, what should we end up here? Well, we need to get rid of this, so we need to have x cubed over a cubed. And now when we distribute this, we end up with minus x cubed, which is what we want. Okay, now compare this with that, right? Instead of x, we have that. So which means in the next step, we can then replace x with x cubed over a cubed, right? Let's do that. But let's not forget this. Let me not forget this factor in front. So x squared over a cubed should be multiplied by, I'm going to modify this side to match this function. Okay, n equals 0. And then, of course, instead of x, we have x cubed divided by a cubed to n power. So now this is going to converge as absolute value of x cubed over a cubed is less than 1. Right? So converges, let me add that, converges when absolute value of x cubed x cubed over a cubed is less than 1. Do you see how these modifications happen to apply the power series, that power series to this one? Okay, it's pretty procedural. It's once you know how the procedure works, it's the same from example to example. Okay, so now let us simplify and distribute this and write it in a way that more series are written in that way. So I'm going to distribute this power into this and then distribute this whole factor into that. So we begin with this. Let's distribute the power first here. So 3n over a to 3n power. Okay. Now we're going to distribute x squared and a cubed. What do we get? We get the series from 0 to infinity x to 3n plus 2, right? Divided by a to 3n power plus 3. Okay, and this is still converging as this condition is true. So converges when absolute value of x cubed over a cubed is less than 1. Okay, so, and let me, so because this is partially answering the questions we were asked to answer. So this is, so this power series represents that function. Now the interval of convergence, we start from this. So we have absolute value of that. Therefore, absolute value of x cubed is less than a cubed. Less than a cubed, and then therefore, so just take the third root of both sides, and we end up with absolute value of x should be less than absolute value of a. So the radius of convergence is r equals absolute value of a, but they asked for not this, but the interval of convergence. And from here, we know that interval of convergence is equal to minus a, well, from here actually. From here, we know that x varies between, as a matter of fact, let me add that here. So we know that the radius of convergence is that, and also that x varies between minus absolute value of a and positive absolute value of a. Okay, so let's put that here. We have minus absolute value of a, comma, positive absolute value of a, like that. All right. Here's the interval of convergence. Let's do another example of this type. These are a little bit different from each other, and that's what makes them interesting. So what do we do here, right? So we have, one thing you should notice is that we have a quadratic function in the denominator. So maybe we can factor that out, right? So let's do that. So this can be written as three over, we can easily factor this. This would be x minus 2 times x plus 1. Now at this point, one thing we should do, because we really need to get this function to look like 1 over 1 minus x, right? We really want this form. If we don't have that form, then our efforts will be very difficult to rewrite this in terms of a power series. So we want this form. Now the only way to get that from here is, we've learned a technique in the previous section that helps us do that, which is find the partial fraction decomposition of this, right? So let's decomposition here. So we end up with, we've done this before. So this fraction can be written in terms of a over x minus 2 plus b. These are easy factors to deal with, x plus 1. Okay, multiplying both sides by x minus 2 times x plus 1, the left-hand side, we get just 3, equaling a times x plus 1 plus b times x minus 2, of course. I'm going to go a little bit quicker here because you've seen this material before. So we have 3 equals that. And then we have a plus b times x plus a minus 2b. Okay, so then we have a plus b should be equal to 0, of course, and a minus 2b should be equal to 3. So from here, we know that a should be equal to a minus b, and then substituting, we have minus b minus 2b equals 3, and then minus 3b equals 3. So from here, b equals minus 1. So b equals minus 1. And then because a equals minus b, so a equals 1. Okay, so now we can rewrite that original fraction in terms of these two individual fractions. Let's do that. X minus 2 and minus 1 divided by x plus 1. Okay, so now take a look at this and compare them with this original power series that we discussed, right? 1 over 1 minus x. So certainly we can rearrange terms and find a power series for these. So let us then, let's do that. I'm going to rewrite this as minus 2 plus x. So let me rewrite that. So we have that is equal to minus 2 plus x. And this one, instead of x plus 1, 1 plus x. Okay. All right, so now we want to put these in the, so let me recall once again. Recall that 1 over 1 minus x can be represented as this power series. Right? So all we have to do is rewrite these such that the format here matches that, and then we'll modify the power series accordingly to find the power series for each of these. Okay, so I'm running out of room here, and you can see I anticipated that, so here it is. I will continue on this page. Like that. Okay, so for this one, all we have to do is factor out minus 1/2 because we want to get a 1. We already have 1 in the numerator. We want a 1 in that as the first number. So let us factor minus 1/2. So we have minus 1/2 times 1 over 1. And then the 2 here, we will get, so minus, all right, that would be minus, to give us minus times minus will give us positive. We'll get minus 2 here and then positive. And then we have to have x over 2 to get rid of that, let's see. Yes, to get rid of this 2 with that 2 that multiplies across to this here. So that would be the factorization of that. Here, we'll have to do some manipulation, but a little less than this. So we have, all we have to do is do 1 minus x. All right? Now, each of these is in this format, so we can manipulate the power series for each one of these accordingly. Okay, so let's replace each one of these with the power series representation. So here we have the factor in front, minus 1/2 times the power series going from n equals 0 to infinity. Now instead of x, we have x over 2. So x over 2 to n power instead of x to n power. Okay, when we had x to n power. So when we have x over 2, we have x over 2 to n power. And then minus, for this one, we have the series. Instead of x, we have minus x. So this will be minus x to n power. Okay. Now each one of these converges at a for a different radius of convergence, or has a different interval of convergence. Let's see what we get. For this one, this series converges when absolute value of x squared is x over 2 is less than 1, right? Like that. How about this one? Well, this one converges when absolute value of negative x is less than 1. Okay, let's solve each inequality for the interval of convergence for each piece. So here we have absolute value of x is less than 2. Therefore, x varies between negative 2 and 2. Here, the negative and the absolute value cancel each other out. We end up with absolute value of x less than 1, and x being going from negative 1 to 1. And so from here, the interval of convergence for this series, we have negative 2 parenthesis negative 2 to 2. For this one, we have the interval of convergence going from negative 1 to 1. So this is that piece, this is this piece, and then, but we can't have both of these. Over a certain interval, they overlap. That's the interval of convergence for the entire series that we have here. Okay, so let's point that out. So here, looking at both of these, we have, let me move this up a little bit. So thus the entire series equation, that means these two together. As a matter of fact, let me put a box around that. So this was the series in conversion of this function that we started with. And of course, this was not factored like this when we started, but so this is the power series for that function. And then here, for the interval of convergence, converges when x belongs to this interval. Again, this is where both of these intervals overlap. Like that. Okay. All right, so in the next part of this section, we will be talking about applying this technique to differentiating or integrating power series. Okay, I included this on this page, which I call 7a, and there's another one coming up after it, 7b, which is closely related to this page, and I wish I could fit all of it on one page because they're so integrated. Then I call these sheets that 7a and 7b. But you can read this as just to be familiar with the notation more than anything, but we don't really have to memorize this. All this is saying, this theorem is saying, it's saying that if you have a power series and you differentiate it or integrate it, the radius of convergence doesn't change. As a matter of fact, I'm making a note of that here. So the radii of convergence of the power series stays the same when the power series is differentiated or integrated. Okay, that's one thing you should remember. The radius of convergence doesn't change through differentiation and integration. It makes things a lot easier. The other thing you should know is that when you are differentiating or integrating a power series, you're doing it term by term. So this is what pretty much this is saying. So if you have f of x equaling that, then you take the derivative of that, and even this side, just like you would take the derivative of any other function term by term. So n comes in front times all of this and reduce the power by 1. And the same thing for each term in this series. Notice that the constant c naught drops out as we go from f of x to f prime of x as we take the derivative of this expression. C naught drops out because the derivative of a constant is 0. And then the derivative of this, C1, if you distribute this into this, C1x is just, derivative of that is just C1. And C1a is, minus C1a is just a constant, so again, it's 0. And the derivative of this piece is 2 times C2 times x minus a2, a power that is 1 less than what it started with before in the original function, right? So again, the radius of convergence does not change as we differentiate or integrate a function. And the differentiation and integration of power series happens term by term, okay, which simplifies a lot what we have to do a great deal. So that's one thing that those are the two things you need to remember from this page. But there are details here. You can read also the notation. You're welcome to just read through this and see what it's saying in terms of the notation, mathematical language there. Okay? All right, so then the next page, which is very important and very integral to our discussion of taking derivative, especially when we take the derivative of power series, is this. So this is a note about the index of a series through differentiation. And of course here then I have additional notes here at the bottom too. But what we ought to know, and this you have to remember, when we take the derivative of a power series, sorry, I was off the screen. When we take the derivative of a power series that represents a function, the index of the series should be increased by 1 for each additional derivative. So what does that mean? This is what we mean by that. So if you start with a series that represents a function, when you take the first derivative, this index value, if you started with, I'm just giving this as an example, but it doesn't matter. If you start from 2 or 3, the same procedure applies. Let's say you started with 0 for the original function. When you take the derivative of that, the power series, the index jumps by 1. And this, if you write out the terms for the whatever expression you have for power series, and then you increase the index by 1, and then you compare the derivative terms with the original terms, you'll see that this matches. It's the way it works, is what I'm saying. But as a rule, this is what we do. For each time you take the derivative, the index jumps by 1. So for the first derivative, it goes from 0 to 1. For the second derivative, it goes from 0 to 2. For the third derivative, it goes from 0 to 3. So for the third, and for the fourth derivative, again, n goes from 0 to 4. Again, this, if the original function started from n equals 4, and you were taking the third derivative of that, you would go from 4 to 7. Just 3, add 3 to that. Okay? All right. And then the other thing we should know is that also, if we wish for matters of simplifying expressions, so this is up to you. When you work with series, if you want to if there is something that you see that you can simplify by changing the indices. The rule is as follows. So if we wish for matters of simplifying expressions, we may reduce. This is when we take the derivative, we're going up, right? So we can reduce the index value for a series as follows. To change this series where index starts from 1 to infinity to one that's the index starts from 0 to infinity, replace every n in the series, not here, replace every n in the series with n plus 1. If you're going from 1 to 0, if you're reducing this number by 1, then everywhere in your series where you have n, replace it with n plus 1. To change from this series going from the index going from 2 to infinity to one that the index goes from 0 to infinity, replace every n in the series with n plus 2. To change a series with index equals 3 to infinity to one that is going from 0 to infinity, replace every n in the series with n plus 3 and so on. Okay, so I've included this sheet and I will post it on Canvas in case you need to refer back to it. But these are the rules. And you'll see these applied in the examples that are coming up. Okay, so here we want to find the power series representation for the function and determine the radius of convergence. Okay, so let's take a function that can make this look like 1 over 1 minus x. Or let me write this down. So let's call it g of x, since this is f of x, like that. Since this is 1 plus 4x squared, let us take one that is with no power. So 1 over 1 plus 4x, right? Since the one that we have is 1 over 1 minus x, we want to obtain something that is similar to that. So which we can write in the form, again, that thing that was on the power series and the associated function that was on the first sheet that we discussed in this section, which is in this form, and has appropriate derivative. And that's one thing we should also look for, and has appropriate derivative. And this one, as you'll see, fits all those conditions. Okay, so we have, starting with this, 1 over 1 plus 4x, and again, we are not including the power yet. So we end up with 1 over 1 plus 4x equals, how can we write this in this form? So it resembles that, 1 minus 4x, right? That's the same thing. And therefore, we can write the power series for this with minus 4x playing the role of x raised to n, like that. Okay. Now, this represents this function that is somewhat similar to this, but not quite, right? We have x there, we have power here, so we're not there yet. So let's take the derivative of both sides. As a matter of fact, let me because, well, because since this represents that, this was useful just to show that why this power series makes sense. But this really, we're interested with this being equal to that. So I'm just going to rewrite it like that. Like this. So now let's take the derivative of both sides. And remember what we said on the previous sheet. When you take the derivative, for the first derivative, that changes to 1. It goes up by 1, right? Let's keep that in mind. So taking, and let's call this equation 1, right? So taking the derivative of both sides of the equation 1, we have, well, let's see, let me grab a scratch paper here. So what do we end up with this one? We have, so 0, derivative of that 0 times 1 plus 4x, right? Minus derivative of the denominator, which is 4 times 1, divided by 1 plus 4x, or whatever the denominator is, squared, right? So we end up with, all of that drops out as 0, so we end up with minus 4 over 1 plus 4x squared, that. Okay, so let's put that on the left side for the derivative of this term, the left side. So we have, let me write this down, minus 4, derivative of that, divided by 1 plus 4x squared. Okay. I didn't want to put all of that here. Anyway, you know about it already, so it was a quick reference to the derivatives. Okay, so now on this side, what we'll get is n comes down, and, well, let's do that. So we have the series, and n comes down, and then we have, before that, before we take the derivative of this, before we take the derivative of this, guys, let's distribute the power. So we have, I should have done that. So minus, I'm going to distribute this. So I have to fix this too. But as a matter of fact, let me do that here. So we have 1 over 1 plus 4x. And on the left and on the right, we have minus 4 to the n power and x to the n power. Let's work off of this rather than that, because minus 4 to the n is just a constant. It's this x to the n that we're taking the derivative of. So now we can look at that. So we have minus 4 to n power, like that, and then n times x to n minus 1 power. Okay, so we've taken the derivative of both sides. Now let's see how we can simplify this. So we have, and by the way, I need to correct myself here, and I'll do that maybe with a thick Sharpie. Since we take the derivative, this has to increase by 1, right, for the first derivative. So this will be 1. N equals 1 there. Okay. All right. So now we have minus 4 to the n and And let's see, so we have, and that, and then, okay, so now we can go back to the original. Since we increased the index, we can go back to n equals 0, but the rule is, in the expression that we have to change this to that, replace every n in the series with n plus 1. Okay, that's if we're just reducing this by 1. Okay, if we had to go from index going from 2 to infinity to 0 to infinity, we would have to replace every n in the series with n plus 2. So everything here should be replaced. Okay, let me actually write it down, even though, so to change the series, or change the index in the series, from n equals 1 to infinity to n equals 0 to infinity, and then, because that's what we original power series is based on, it's from 0 to infinity, and it makes sense here. Sometimes it makes sense if we keep it at 1 or even 2. So to that, we'll have to every n in the series with n plus 1. Okay, and that way we can change this back to 0 in the derivative. Okay, so let's do that. And we will have this. We will have, I will still keep this. Notice that we still have not dealt with this x, okay? We will have to then account for that later. For now, we're dealing with, we have something here, minus 4 over 1 plus 4x squared, that is somehow looking like this, but not quite. But we'll take care of this x in a bit. So for now, this minus 4 divided by 1 plus 4x squared. So we're going to switch this from 1 to 0. Now every n in the series is replaced by n plus 1. That one and this one too. And also that one. When we replace this n with n plus 1, we just get plus 1 and minus 1 cancel out. We just get n x to the n power. Okay. All right, so let me move to the next page here. Okay. So we can then rewrite the original function based off of this. Original function as, and I will, because it's off the screen, this is what we started with, x over 1 plus 4x squared, right? So we need to multiply this side by something that would give us x over that. The denominators are the same, but the numerators are different. We want, so this is equal to minus x, because we need to get rid of this minus, right? we have positive x in the numerator. So minus x divided by 4. If you multiply this by that left side, you will get positive x over that. The 4 will cancel out, the minuses will cancel out, you get x over that, which is what we have in this function. So minus x over 4 times that, minus 4 over 1 plus 4x squared, like that. And we'll have to do the same thing to the power series that we have, because the power series and this function are equivalent. We multiplied the left side by minus x over 4 to get this, so we multiplied that power series by minus x over 4 as well. Hopefully I can fit it all in here in the space that I have left. So that is equal to minus x over 4 times the series going from 0 to infinity, and we have minus 4 to n plus 1 power, and times n plus 1 times x to the n power. So barely I was able to do that. So now, of course, we have, we can maybe simplify these terms a little bit and get rid of these, so to do all that. So let us do that. We have this minus 1. I'm going to write this, I'm going to separate this minus 1 to, and write it separately than the 4. So let's do that. I'll give myself a little bit space here. But this is what we're simplifying. So we have minus x over 4 times the series. And so I'm going to put minus 1 to n plus 1. I'm just separating minus and the 4. And then times 4 to n plus 1 power. And then n plus 1, I'll keep it for now, times x to n power. Okay. I don't think we need that sheet anymore, so like that. So now there's a bunch of things we can simplify, and let me do that like this. So we have, I'm going to keep this minus x over 4 in front. Then that. So I'm going to, once again, separate minus 1 to n power from minus 1 to power 1, right? I broke this up into 2 pieces. And then, because I want you to see exactly what happens before we can simplify this. So you probably don't need this, but I'm just making sure that if anybody has any questions, they get them answered when watching this video. So I did the same thing with this. I broke this up into these 2 terms, and then n plus 1 times x to the n power. Okay. Now, what can we simplify? Well, we have a minus 1 here and a minus here. Right, so that, oh, and the left side, of course, is x over 1 plus 4x squared. Same thing here. Sorry. So, well, I don't have a white out here, but this is 1 plus 4x squared. I will fix these notes before posting them on Canvas. And I apologize for this. So this is the whole parentheses, 1 plus 4x squared. Okay, and I will correct this. And so then on the other side, we have this 4. Notice that this 4 and this 4 cancel out. This minus and this minus cancel out. They become positive. And we have an x here and an x to the n power here. So when we combine them, we get x to the n plus 1 power, right? So let's rewrite this. We have minus 1 to n power, 4 to the n power, we have that doesn't go anywhere, and then times n plus 1 stays 2, but this x to the n and this x give us x to n plus 1 power. Okay, so this is then the power series representation of the function that we started with, and we had to use differentiation there in the middle. Again, I apologize with that. I will make sure that this is pretty legible before posting these lecture notes on Canvas. Okay, so now we'll have to find the radius of convergence. I think is this time there's, yes, radius of convergence. So that goes back to what we mentioned earlier, that the radius of convergence does not change through differentiation and integration. So I want to bring this note to your attention. The radii of convergence of the power series stays the same when the power series is differentiated or integrated. Okay, and this is, I have an error here, differentiated or integrated. I need to make that dictation correction. So let me just here make a mention of that. Does not change for different representations of the same power series. Okay, so we know that for this, so what we had, maybe I can find it here quickly. When we had that, remember this is what we started with, right? This was the initial function g of x that we started with, and then the associated power series with that was this, minus 4x to the n. So the radius of convergence was this. Maybe I should actually add that. Converges when absolute value of minus 4x is less than 1. Okay? I should have added that right there when I was writing this. This is pretty important. So this doesn't change. Throughout this procedure, what that theorem was saying is that this radius of convergence doesn't change, so which is 1. So this absolute value of this quantity less than 1. So we still, thus, the absolute value of convergence here, we still have minus 4, absolute value of minus 4x less than 1. So let's solve for that. So this would be 4 times absolute value of x less than 1. And then, of course, absolute value of x is less than 1 over 4. So radius of convergence is 1 over 4. Okay, this is that. All right. Okay, so let's see another example here. So this time we want to rewrite this function as a power series, and also we want to find the radius of convergence. So go ahead and attempt this on a piece of scratch paper, and then look back at the video and see how your solution agrees, or is it different than this one. Okay, so looking at this, just looking at the denominator, it looks like we can choose our base function to go with for this with 1 over 2 minus 6, because that's closest thing we can find as a connection between this and 1 over 1 minus 6, which is that, right? We're still working off of this, 1 over 1 minus 6, this power series with this radius of convergence. So maybe 1 over 2 minus 6 is a good place to start with. I'm going to do that. So the expression 1 over 2 minus x. Okay. All right. So then we can write, let's rewrite this so we need a 1 there, right? And that's minus is good, that's x is good, but we need to have a 1 in that corner, or that as that first term in the denominator. So we need to factor that. So 1 over 2 times 1, and then that would be minus x over 2 there. Okay, so what do we have? We have 1 over 2, factoring that out, 1 over 2 times 1 over 1 minus x over 2. Okay, so that then I can add it here, but maybe well, let me write it here. So then we have to write this. So on the power series side, 1/2 times the power series starting from 0 to infinity. Instead of x, we have x over 2, right? So this will be parenthesis x over 2 to n power. I skipped writing this, but I hope you see what I'm doing, right? I skipped writing this time. 1 over 1 minus 6 is equal to this power series. Okay, so instead of x, we have x over 2, so that ends up there to n power. So now let us then distribute this n to each term here and just get x to n power. Okay, so we have, so thus this, what we started with, is equal to 1/2 power series. We're gonna, this 1/2 comes from there, but there is a 1/2 there too, right? But that one has a power n times x to n power. Okay, like that. Now this 1/2 to n power gives us 1 over 2 to n power. We have a 2 here. Let's combine this with that. We get 2 to the n plus 1 power. Right? So we have then 1 over 2 minus x can be written as, I want to include this 1/2 as part of that. So we have 1 over, 1 to the n is just 1. 2 to the n times 2 to power 1, we get n 2 to n plus 1 power. And then, of course, the x to the n. Okay, like that. Let's call this equation 1. I'll just call it with I, equation I. So notice that this is, we can differentiate this and get something that is closer to the original expression we have. We're not going to have this because this has third power is to power 3, so but we still have to work our way such that the power series on this side is more representative of what we have here. Right now we have quite a ways to go. This is just 1 over 2 minus x. So if we differentiate the left side, you know that we're going to get 2 minus x squared, at least in the denominator. And that is a little bit closer to 2 minus x cubed, which is what we have here. So let's do that. So differentiating both sides, including the power series. Remember, when we do that, this is going to go from n equals to 1, right? It's going to change. So differentiating both sides of equation I, we have 1 over, so, well, let me grab my scratch paper again. So on the left, what do we have, right, for this piece? The derivative of that would be just 0 times 2 minus x minus 1, which is the derivative of this, times 1, divided by 2 minus x squared, right? So this will be drop out as 0. This will be minus 1, which is 1. So we end up with 1 over 2 minus x squared. Okay, so we will have that. 1 over 2 minus x squared equals, now we have to differentiate the right side. So this is going to go from n equals 1 to infinity, right? This is what we were talking about on that sheet that talks about the indices of series as we differentiate and such. And then that becomes n times x2 n minus 1 times all of that, which is considered a constant when we take the derivative. So we have 1 over 2 to n plus 1 power times n times x2 n minus 1. Okay, so let's call this equation 2 or double I, like that. So note that what we have on the left is still not 2 minus x cubed, right? If you distribute this power into these two terms, we get x cubed over 2 minus x cubed. We're still not there. So we need to take the derivative of this again. Let's see. So if we do, so we have, so if we do that, what are we going to get? So let's see. So we will have the derivative of that will be, so again, 0 times 2 minus x squared, then minus derivative of that would be 2 times 2 minus x to power 1 times, by the chain rule, times minus 1 over 2 minus x squared, right? So this drops out as 0. This we will have 2 minus 2 times minus 1. We end up with 2 times 2 minus x, and raise that to squared, right? Raise all of this 2 minus x squared squared. So we will have 2 minus x to 4th power. And then this and this cancel. We get 2 over 2 minus x cubed, right? That would be the derivative. This is going to be the derivative of that. The second derivative of the original function that we picked, but the next derivative of this. So on the left, we're going to have this. And sorry, I didn't want to put all of that work here. It's not needed, right? You already know that. And I want to make sure that you have this in your notes. So note that our original function is raised to power of 3, right? We have this, f of x equals x over 2 minus x cubed. So to obtain that power, we must differentiate equation 2 again, this equation again. Again. So, and I did that in that scratch paper. So what do we get for that? We get, let me move this up a little bit. We get 2 for the left side, 2 over 2 minus x cubed, right? After simplifying. On the right, let me bring this down. I'm trying to include all of this on the screen. So when we take the derivative of the right side, this will increase again, right? It went from 0 to 1 when we took the derivative to get here. So this is going to be n equals 2. Okay, and then n equals 2. And then we have, again, this is going to be our constant. So we have 1 over 2 to n plus 1 power times n, this time n minus 1, right? N minus 1 times x to n minus 2 power. Just taking the derivative of this, the right side, the power series with respect to x. Okay, I hope this is making sense what we did and how the indices change. So we know that in order to go from this, we'd like to keep this indices. It's better to keep the indices to 0. So we're going to revert back to 0 for this derivative side of the power series. And you know that because this is 2 to 0, we're going to have to replace every n with n plus 2. Right? It's on that sheet. So if you have any questions, please refer back to it and let me know if you have any questions. So let me actually, I hope I can fit it here. So to start, this from 0, right? Instead of 2, we wanted to start from 0 in here. So we need to replace every n in here with n plus 2. Okay, so let's do that. Can I fit it here? Maybe I can. I'll just give it I think there's enough room here. So on the left, we have the same thing. We have 2 over 2 minus x cubed. On that side, we want to change this to start from 0. So now, everywhere here, where I see n, I'm going to replace it with n plus 2. So we're going to end up with here, n plus 2 plus 1. It is going to be n plus 3. So 1 over 2 to n plus 3 times, instead of that, n plus 2. Instead of that, n plus 2 minus 1, it's n plus 1, right? And then n plus 2 minus 2, minus 2 and 2 cancel out. We just get x to n power. Okay? So, now we're getting where we need to be, because if you compare this, the left side, with what we have started with, we have 2 minus x cubed now. But the numerator, of course, is x. We need x, not 2, right? So we need to multiply the left side by a factor that would get rid of the 2 and give us x. And that would be x over 2. So we're going to, in the next step, we're going to multiply both sides by x over 2, this side and that side. But before that, maybe I should a little bit simplify this. Can I simplify this? Let's see. Yeah, maybe I can just combine this into just one fraction. I'll do that too. Let me do that here. Okay. So simplifying the right side a little bit. And then we're going to pretty soon we're going to multiply both sides by that. So simplifying. The right side. I'm sorry. I'm just thinking about something that I just saw. So to get what we want, we'll have to multiply this. I know I said, I think x squared over 2, it's x cubed over 2. Because we need an x cubed here, and we need to get rid of the 2. So it's multiply both sides by x cubed over 2. Okay, the right side by... we have this. So we have... the left side stays the same. And so we have just all of that divided by 2 to n plus 3 times x to the n power. Okay. So now for the original function, which was this, f of x equals x over 2 minus x cubed, we must multiply, I guess let me call this equation 3i, triple I. Okay, we must multiply oops, sorry, we don't need that sheet anymore, so let me move this up. Multiply both sides of equation triple I by, we want this, we have this, right? So we need to get rid of the 2. So we should have a factor that has 2 in the denominator. We want x cubed. So we should have x cubed in the numerator. Okay? All right, so let's do that. And we end up with, so x cubed over 2 times that, right? 2 over 2 minus x cubed. And this is equal to doing the same thing to the power series side. So we have x cubed over 2 times n goes from 0 to infinity of all of n, the rest of it. So n plus 2, n plus 1 over 2 to n plus 3 times x to n power. Okay, so now the original function that we have, this 2, right? This 2 and this 2 cancel out. X cubed over 2 minus x cubed is the same thing as that, right? If you distribute the power, we get that. We get what we have. So on the left, we have x cubed divided by 2 minus x cubed, which is equal to, I still like to rewrite it just like what we had at the beginning. So 2 minus x cubed, right? That's what we had, right? Yes. So this is equal to, and so we have an x cubed here and a 2 here. So we can distribute all of this into this, right? And change this power series accordingly. So we have n going from 0 to infinity. And then these two don't change. We have n plus 2 times n plus 1. Because of this 2 multiplied by this, we're going to have 2 to n plus 4 power. And because of this x cubed, we're going to have x to n plus 3 power. Like that. Okay. All right, so this is, we've achieved here, we've achieved the power, we've obtained a power series representation of the original function that we started with. Okay. Now, I think I forgot to do it here again. Sorry about that, but see, what we started with, which was 1 over 2 minus 6, had this power series, and the radius of convergence for this power series was x over, absolute value of x over 2 less than 1, and then we'll have to calculate that. It would be, r would be 2. But I didn't do it here. But the point I'm making is that that's not going to change. That radius of convergence throughout this procedure does not change. That's the important thing to remember. So I should, however, there's not much space for me to write that, but let me write it here. I'll refer back to it. So recall from this expression that we had, 1 over 2 minus x, which was represented by this power series. This power series that the series converges, this series converges when absolute value of x over 2 is less than 1. So that does not change throughout this procedure. So, and the same is true. So the same is true for the power series, for this one, for so that is, so we can easily then say that absolute value of x over 2 less than 1, absolute value of x less than 2, therefore r is equal to 2, radius of convergence. They don't ask us for interval of convergence, so we stop there. Okay. Okay, so let's do another example. Like that. So this is a little bit, it looks like more straightforward than the previous one, right? So if you look at the denominator, it's already in form 1 minus x. So what I would start with here would be with 1 over 1 minus x. Sorry, I had to drink a little bit of water here, but okay, so let us start with the original, the power, this power series. So let us start with 1 over 1 minus 6, which is represented by this power series, right? We start with that. And then here, notice that we have 1 minus x cubed, right? So if we don't differentiate this, there's no hope of getting to that power. So we need to differentiate this to obtain a higher power and a higher power. Okay, so let's do that. And when we do that, I'm just going to grab my scratch paper again. So if we differentiate this side, what do we get? We get 0, the derivative of the numerator, times 1 minus x minus 1, which is the derivative of the denominator, times 1 divided by 1 minus x squared. So that term cancels to 0. Minus 1 is just 1 over 1 minus x squared. So this is better. So we're working our way to starting with this, but then moving up to that power. Okay, so differentiating both sides of this, and I will just call this equation 1 this time. My dictation is suffering here. So differentiating both sides of equation 1, and as you saw, we end up with 1 over 1 minus x squared for the left side, and for the power series side we end up with, remember that the index goes up, right, every time we obtain the derivative, the next derivative. So n equals 1, and then n times x to n minus 1 power, right? So let's see. So now that we have the derivative, let's revert back to the index being 0 again. And we know the rule for that, right? We need to replace every n with n plus 1. To that, and so let me call this actually equation 2. So we must replace every n in equation 2 with n plus 2. Sorry, n plus 1, I meant. N plus 1. I have to go over these sheets again and make the corrections with a whiteout before posting them on Canvas. I will correct that. So that's n plus 1, not n plus 2, n plus 1. Okay, so now let's do that. So we will have 1 over, let me move this up, equals n equals 0, right? Now we're replacing that with n plus 1 and times, let's see, so that, and then replacing that n with n plus 1, minus 1 and plus 1 cancel each other out, we just get x to the n back. Okay, so that's that. Okay, so now if we want power 3, we should differentiate this again. And let me bring my scratch paper back because I don't want to write the derivative work for the left side on this paper. If we differentiate the left side, will we get, do you think will we get this, 1 minus x cubed in the denominator? Let's find out. So the derivative of that would be 0 times all of that minus the derivative of the denominator and times minus 1 by the chain rule times the numerator divided by 1 minus x squared, right? So if we simplify, this one drops out as 0. Minus 2 times minus 1 is positive 2. So 2 times 1 minus x divided by 1 minus x to the 4th power, 2 into 2 raised to 2nd power, 4th power. But this and this cancel and they give us 2 over 1 minus x cubed, right? Which is what we want. We want 1 minus x cubed, which is what we have here. Great. So we should differentiate again to get 1 minus x cubed on the left side. And I will, with n plus, and I will call this equation 3 actually. So to obtain 1 over 1 minus x cubed, we must differentiate both sides of this equation again. Equation 3 again. Okay, so we already know the left side, what it will look like. So it is going to be 1 over 1 minus x cubed. And So this again, so we're going to reduce or increase this by 1 again. And so we will have n equals 1 from in the index. And then we will have n plus 1 times n times x to n minus 1 power. Right? And then, so we want to, again, we want to go back to the index starting from 0. So, or let me, so we're going to replace, if we want to go from 1 to 0, we're going to have to replace every n with n plus 1. Okay, so let's do that. So, or to start the index, or to start the index from this rather than that. And I forgot to bring my highlighters, so otherwise I would have highlighted here and here. So we want to start the index from n equals 0, and right now it's 1, rather than starting from 1, which is happening right now. So to do that, replace every n with n plus 1. So because it's just one n value, one integer. If we were going up 2, if we were going from 2 to 0, then we will have to replace every n with n plus 2. Okay, so we must replace every n, and let me call this equation 4. In equation 4, with n plus 1. Okay, so let's do that. Like that. So we have 1 over 1 minus x cubed equals index going from 0 to infinity, right? Switching from 1 to 0. So if I replace n with n plus 1, n plus 1 plus 1, it's going to be n plus 2. If I replace this n with n plus 1, that's what we're going to have, n plus 1. And if I replace this n with n plus 1, we have n plus 1 minus 1. We end up with x to the n power again. Okay. So now this, let's call this, do we need to call this, let's see, any equation. Okay, so far this is where we are. Now looking back, let me go to the next page here. Like that. All right, that's okay. So looking back, let's see. I will probably need another page too. So looking back at our original function, we had, this is what we had, x squared plus x over 1 minus x cubed, right? This is what we have so far, or represented with a power series, but this is what we have. We can easily break this up into x squared over 1 minus x cubed plus x over 1 minus x cubed, right? We can just do that easily to over common denominator. So now to get that, to get this from that, then we'll have to multiply that by x squared, right? So by x squared, and then let's see, so we have this is, let's see, suppose we have, I think I should, so one of these, I need to make a correction, everyone, to the numerator to one of these, that one. So when I took the derivative of this, I ended up with 1 over 1 minus x cubed, and that's not correct. Let me show you why. So if I made an error there, I want to correct it here. So if we take the derivative of this left side, we have 0 times 1 minus x squared, right, minus the derivative of that will be 2 times 1 minus x to first power times minus 1 by the chain rule times 1, right, over 1 minus x squared squared. So this drops out to 0. Minus 2 times minus 1, it's going to be 2. It's going to be positive 2 over, or 2 times 1 minus x over 1 minus x to fourth power. And then simplifying that, I get 2 over 1 minus x cubed, right? That, and so 2 over 1 minus x cubed. But I have 1 over 1 minus x cubed. So that's where the error happened. So let me correct that. So let me correct that with this thicker marker. So this is 2. This should be 2. And this should be 2, this one also. So, and then, so exactly, so this should be 2 as well. And this should be 2 as well. This should be 2 as well. Okay, so now, so this is what we have so far. And looking back at the original function, if I want to get this from that, I'll have to multiply that by x squared over 2. The 2's cancel out. I end up with x squared over the denominator here. So I will do that. So therefore, we will have x squared over 2 times that. That because we have a power series representation for that. So we're going to connect this to that by multiplying it by this times that, which we have on the left side. So we have 2 divided by 1 minus x cubed. Okay, plus x over 2 for this one. To obtain this from that, we need to multiply that by x over 2, right? So x over 2 times, again, that 2 over 1 minus x cubed. Okay, so now instead of that, since we did this to the left side, we should do the same thing to the right side, right? To the power series. So we're going to do that. Well, I can't remove that sheet yet. I'll try to keep it on the screen. So now we have x squared over 2 times, instead of that, I'm going to put that power series. So we have power series from 0 to infinity, n plus 2 times n plus 1 times x to the n power, plus x over 2, again the same power series. So n plus 2 times n plus 1 times x to the n power. Okay, now we can remove that sheet, and that has all the information. Okay. So now, let's see. So we have, we can simplify this, right? Because we have x to the n power, and then we have x squared. So we can combine those two. We can distribute this into that. We get x to n plus 2 power, everything over 2. Okay, so let's do that. So we have, so distributing both of these into the power series, we have, so we want to, so this is the logic behind what we're doing. So notice that the exponents on x, let's see. On x will change. Right now it's x to the n, x to the n. And so change as we distribute x squared 2 and x over 2. Okay, so what are we going to get? We're going to get this. We have x squared plus x on the left side. That I'm rewriting that. And we have, let's see, so over 2. Let me, so you can see this, what I'm doing. So then it'll be, so I put this 2 underneath that, and then x times x to n plus 2 power, n plus 2 power, plus that, and then again n plus 2 times n plus 1 over 2 times x to n plus 1 power. Okay, and that's distributing the x to n power. We get that. Notice that once before this, what we did, the x's had the same power here, but we had to distribute that. So now they have different power, right? So let me add some comment here. Exponents on x are not equal. if we want to simplify our series, we want to keep the indices the same, and if the x terms have equal power, it would help us simplify the expression if these are like that and the x powers are the same. So let's see, I think it's better to make those powers equal. So right now they're not. So x are not equal. So let's make them equal. Equal to x to n power by changing the indices of the series. Indices being these values, n as n changes from 0 to infinity. So if we want to get n, n equals, or x to the n power here, we'll have to increase this by 2. Just like when you take the derivative, right? When you take the derivative, this drops by 1, so this goes up by 1, right? That's what we did in the previous examples. So n plus 2 minus 1, n plus 2 minus 2. So for each reduction in this power, this will go up by 1 unit. So then, so if we want to keep these x to the n, so this will jump by 2, and that one will jump by, that should jump by 1. Let's see. So we have, let us see. Well, if we want to keep this to n, well, let us see in the next step. So I have x squared plus x over 1 minus x cubed on the left. And then we have, so we have infinity. So this will go, this will become 2. Right? And then we're going to replace each of these with n minus 2. So instead of n, we have n minus 2. n minus 2 plus 2, that'll be n. And replacing this, n with n minus 2, we get n minus 1. And that will be over 2. And then x, replacing that with x, that n with n minus 2 to get x to the n power, right? That's our objective, to get x to the n power for both of these guys. Now we have that here, and the way we were able to do that, we changed the index by 2, we increased it by 2, and we replaced, everywhere we have n, we replaced it by n minus 2. Okay, now we have that. Now the other one, so we want to get x to the n power here as well, and we'll have to replace n with n minus 1 this time, and that will increase this n by 1. So we have, going from 1 to infinity, replace this with n minus 1, we get n minus 1 plus 2, we get n plus 1. Replace this n by n minus 1, n minus 1 plus 1, we get just n over 2. And replace this n with n minus 1, we get just x to the n power. Okay, so now in this series, in this one, notice that if we move this, if we simply calculate the first term for this, right? What happens is that we're going to get this to be 2 because we've calculated this, the first term for this series. And then we're going to get an x. So simply, let me actually, so notice that I'm just going to make a note of it here. Notice that when n equals 1, in this series, that means when we're calculating the first term in this series, the first term in this series, so when n equals 1, what do we get? We get x to the 1 power x. 1 plus 1, 2n. 2n over 2. 2's cancel out, and n is just 1, so 1 times x is just x. So the first term in this series, if you calculate it for n equals 1, you get x is x. If we do that, what will happen is that that will help us change this index to 2. Okay, so let's do that. And that will be, then this is n equals 2, that is n equals 2. So then we can combine terms like that when the indices are equal. And especially when the x terms have equal power 2. Okay, so we can the objective of what I'm doing is to simplify this series. That's all. Okay, so if we do that, I'm just going to write it here. We have x squared plus x divided by 1 minus x cubed on the left. And this we have, let's see, so we have n equals 2. And then let me also distribute this. I'm going to distribute. Again, the objective of everything is just to simplify this massive series. And so n times n is n squared. N times minus 1 is minus n over 2 x times x to the n plus this x plus, I'm just going to write everything that is connected to in red so that you know what's going on moving from here to here. So plus x plus, now that's going to jump because I've already calculated the first term for this series, which is x, which I've written here. Now this has to start from 2. And then we have, let's distribute this as well. N times n is n squared. N times 1 is n over 2 times x to the n power. Okay? All right, so now I'm going to write everything individually so you can see the terms that will cancel out. And maybe I should grab another extra sheet here. If you bear with me, I will grab a blank sheet here. Okay. So on the left, we still have the same thing, x squared plus x over 1 minus x cubed. So let's separate these. So we're going to have, let's see, so we have x, well, I'm just going to put this x at the beginning. So this x, and by the way, so from here, what changed was this index 2. This is 2. Okay, so I'm just going to put the x here at the beginning, plus, let's separate these. I will have index. Notice since the indices are the same and the x term is the same, we can simplify terms. And that's the nice thing about what we did so far. So we have n squared over 2 times x to the n power minus n over 2 times x to the n power, right? Plus we've already accounted for this x here. So we have to worry about this, and that gives us, so we have n squared over 2 times x to the n, right? I'm just separating this, plus one more term, and we have n over 2 times x to the n. Okay? So now we can begin to simplify the right side, the left side, and we can get rid of that sheet there, like that. So we have x squared plus x divided by 1 minus x cubed. We have this x here, and then can we get rid of this? No, there's no n squared. Whoa, there is 1 here, right? So we have n squared. So we can combine this with that. How about this? Well, this one and this one cancel out. So these two, that term and that term cancel out. We end up with x plus. These two can be combined. So we have n squared over 2 plus n squared over 2, right? N squared over 2, n squared over 2 times, of course, xn. X to the n power, I mean. Okay, so now that can be simplified further. It's just 2n squared over 2, which is n squared. 2 and 2's cancel out. We end up with n squared times x to the n power. So let's write that down. Like that, n squared times x to the n power. So if we, so for n equal 1, so for n equals 1, right, if we calculate, well, let me write this as a comment here. Note that, because we can still combine these two, and here's why. Note that for n equals 1, this series, n squared, I'm not going to put the index, this because so you can see what I'm trying to make a point with n equal being 1. This expression equals 1 squared is just 1, x to the 1 power is just x, so this series will be equal to x. So if we take this series, this piece from n equals 1, we're accounting for that too. Right? So let's do that. We can combine these two by starting the n from 1. Okay, thus, therefore, so from there we have x squared plus x over 1 minus x cubed equals n equals 1 to infinity. And now we have our series. So this would be the power series representation of that. So in the middle, it was a little bit tedious, I know. In the middle was quite tedious. We had to go through all that, change the indices and change the powers of x to match so we could simplify the terms. But in the end, it paid off nicely because now we have pretty good power series representation of this function. Okay. Of course, we need to also give the radius of convergence. And if we look back at what we started with this expression, right? 1 over 1 minus x, which of course we know converges for absolute value of x less than 1. Now that theorem that we have tells us that the radius of convergence does not change through all of this work that we did. So therefore, so we can say that let me write a short note here. We know that r equals 1 for this expression that we started with. Right? We know that. And the same is true for the power series, for the series this that we ended up with for our function. Thus, r equals 1. Okay, radius of convergence. Okay, so everything we did, these past 2 or 3 examples that we did, talked about applying the derivative to finding power series that represent functions. But now, how do we use this with integration? So let's do a few examples of that. So here we want to evaluate the indefinite integral here as a power series. What is the radius of convergence? So we want to rewrite this integral as a power series. Okay. So first of all, note the integrand, right? It's t over 1 plus t cubed. So it looks like we can rewrite this as 1 over 1 plus t cubed, right? We can start with that. So let's do that. So we can the integrand as follows. So we start with t over 1 plus t cubed. And this is, so let's factor out the t times 1 over 1 minus t cubed. So I'm skipping all those steps where I refer back to the power series that we discussed on the first sheet, right? I'm not making a reference to this anymore because after all these examples, I'm counting that you'll remember what you're making the connection between what I'm doing and what this is, right, on the first page. So that's what we're headed here. And we factored the t out. Now we have 1 over 1 minus this, which means that now we can rewrite this piece as a power series multiplied by t. Okay, so let's do that. So knowing that 1 over 1 minus x, well, I guess I'm referring back to it here. And I'll just call this equation 1. as, so 1 plus t cubed equals t times, I'll just put the power series here, times 1 over 1 minus. So multiply this side, we have a factor t right here, right? So t times the power series from 0 to infinity, and then instead of x we have minus t cubed to n power, right? So then if we can write that integral, or that integrand, not the entire integral, but this piece, and I wish I had my highlighter, just this piece, the integrand, that piece, as that power series, right? And let me actually, I should distribute this t since we're going to integrate the power series in the next step. So let me do that. So distributing this t into that and separating the minus 1 to n power, this is what we're going to get. To n power, that's this minus to n power. And then distribute this t into that, we get, this is 3n plus 1. So this is just the integrand, not the integral, right? This is that. This is a power representation of what's inside the integral, the integrand, as we call it, right? So then to integrate this, to integrate that, it's to integrate the power series that we have, right? And the procedure is exactly the way we've done it with integrating terms like this. So we add 1 to this power and divide that by the whole thing by the new power. So let's do that. Thus, the integral of the left side, which is what we have, dt, would be the integral of that. Of course, integral of that will get because this is an indefinite integral, so the rules apply here to the series part, which is we're going to get a constant, right? Plus, then this will be 3n plus 2 divided by 3n plus 2. Right? This is how we would integrate x. x to add 1 to the power, divide that by the new power. So this is what we're doing. The new power is that, divide this by the new power. So there we have it. This is the power series. This whole right side represents this indefinite integral. And they also ask for the radius of convergence. And the radius of convergence, of course, is that absolute value of minus t cubed. Right? That's pretty straightforward. So it comes from that. So note that the series this converges when absolute value of minus t cubed is less than 1. Of course, if we take the absolute value and the minus, that gets rid of the minus, absolute value of t cubed, less than 1. And this is simply take the third root of both sides. We still get absolute value of t less than 1. So the radius of convergence for the series that represents the integral is 1. Thus, r equals 1. This is the radius of convergence for the series that represents our integral. Okay, let's do another example here. So we have this expression, and this goes back to one of the examples that we did in the book, actually, the book, so I will refer back to that. So let me do that. Note that the derivative of natural log of 1 plus x is 1 over 1 plus x, right? We know that, like that. So we can write that. I guess you're seeing where I'm going with this, right? So we're going to connect this with the power series we've been discussing throughout this section. So 1 over 1 plus x is equal to 1 over 1 minus x, which gives us this power series minus x to n power. Okay, so, or we can write this as minus 1 to n power times x to the n. Okay, so now, and so let's see what the first few terms of this look like. Okay, and power series are, so we have 1 over 1 plus x is equal to, so for n equals 0, this becomes just 1, and that's just 1, so we get 1. For n equals 1, we get minus, and then this would be just x, so it will have minus x, right? So then for the n equals 2, what do we get? We get minus 1 squared is just 1 times x squared plus x squared. And then for n equals 3, we get minus 1 cubed is just minus 1 and minus times x cubed, and so on and so forth, right? So if we integrate both sides, if we integrate both sides of this, what will we get, you wonder? Well, we'll get a power series representation of this piece. Because if we integrate this, we're going to get that on the left. On the right, we're going to get a power series representation of that piece. Okay, and then we can integrate that. So that comes from this. So let's, so integrating both sides, I'm just going to, so integrating both sides. This is just what I said now. I'm just going to write it to be sure that you have it in your notes. integrating both sides. So what do we have? We have, of course, this we know is natural log of 1 plus x. Integrating that, we get x. Integrating that, we get minus x squared over 2. Integrating that, we get x cubed over 3 minus x to the 4th over 4 plus on and on. Okay. All right, so now, so this is represented by, let me write this down. So this is, we have minus 1 and plus 1 over 1. So this is natural log of 1 plus x, and we have equals, so we have C. So we have this equals 1 minus 1, let's see, minus x to n power, and so we have minus 1, and then we have 2, let's see, so we have n minus 1, so this will be start from n equals 1, and that, and then times x over n plus c. So if you, this being the power series representation of this, so for n equals 1, what will we get? Right? For n equals 1, it's just looking at that, we can write that. Right? So we have 1 minus 1, 0, that drops out. Minus 1 to 0 power is just 1. X to 1 power is just x, over 1 is just x. For x, for n equals 2, this will be 2 minus 1. Minus 1 to 1 power is just minus, and then x squared over 2. So notice that from here we can come up with this series interpretation of that natural log of 1 plus x, just looking at the individual terms. So it helps out if we write the individual terms like that. Now, and of course this will converge when original, this also converges when absolute value of minus x is less than 1. So let me write that down, which converges when absolute value of minus x is less than 1, or absolute value of x is less than 1. Okay? All right. So now our original function was not just this natural log of 1 plus x, but it was x squared times natural log of 1 plus x. Okay? So let's multiply both sides by x squared. Okay, so we're going to let us multiply, well, I will write that here. Both sides by x squared, we will have, on the left, we have x squared, natural log of 1 plus x, right? On the right, let's just distribute that to this one. So we'll get x to n plus 2 power. Over n, right? So now, because the integral we have is integrating what we have on the left side there, so we can integrate both sides of this equation. So integrating both sides of this equation. So on the left, we have integral x squared natural log of 1 plus x dx. On the right, we can do what we used to do whenever we integrated x terms. So we will do x to n plus 2 plus 1. It will be n plus 3 divided by that new power, which is n plus 3, which is n times n plus 3. So we have, let me write that. And of course, since this is an indefinite integral, we're also going to get a c here, c term plus that minus 1 to n minus 1 power, and then so x to n plus 3 divided by this n times n plus 3, like that. Okay. Okay, so this is basically our power series representation of this integral, like that. And of course, we have to give the radius of convergence. So let's say a few words about that. So notice that r equals 1. R equals 1 is the radius of convergence for the series that represents that natural log of 1 plus x. Okay, and it all comes from here. Absolute value of negative x less than 1 is the same thing as saying absolute value of x less than 1, which means radius of convergence is equal to 1. So that represents natural log of 1 plus x for this, and the same is true for the series that represents x squared times natural log of 1 plus x. And thus, for integral of x squared natural log of 1 plus x dx. Okay, so thus r equals 1. Again, this goes back to that theorem page that I said you don't have to memorize, you just have to remember those few things, that when we differentiate and we integrate the power series, the radius of convergence for the functions they represent does not change. So this goes back to that. All right, so this is this example. Let us do another example. stuck. Okay, so here's the next example. We have an inverse tangent function. Interesting, isn't it? So the first thing we want to remember is that what is the derivative of the inverse tangent? So recall that the derivative of the inverse tangent is equal to 1 over 1 plus x squared. Okay. So we can write this in terms of 1 over 1 minus x squared, right? Let's do that. Thus we can write 1 over 1 plus x squared equals 1 over 1 minus x squared, right? This would be 1 plus x squared again. Okay, so then in our familiar power series, which we showed on the first page of this lecture, so this would be n equals 0 to infinity, and then instead of x to n power, we will have minus x squared to n power, right? So therefore, we can say 1 over 1 plus x squared is equal to, let me clean this up a little bit, so we will have minus 1 to n power, and then x to 2n power, like that. Now, to obtain a power series representation for inverse tangent, all we have to do, since we found a power series representation for the derivative of inverse tangent function. So if we integrate the left side, we know what we're going to get. We're going to get inverse tangent. On the right, we're going to get a power series which will represent that inverse tangent function. Okay, so let's do that. For inverse tangent x or arctangent x, we can integrate both sides of this equation. Maybe I can call this equation 1, both sides of equation 1. Okay. All right, so if we do that, let's, on the left, we're going to, okay, like that. We will have inverse tangent of x equals integral of 1 over 1 plus x squared dx equals, and then how do we integrate the power series? Very easily. We just add 1 to it, 2n plus 1, divide that by the new power, which is 2n plus 1. Like that. Of course, the radius of convergence, again, is based on that original representation function that we picked. So in this case, it would be absolute value of minus x squared less than 1, right? or absolute value of x equals 1. Let's actually mention it here. So where the radius of convergence r is as follows. So absolute value of minus x squared less than 1. And again, this is coming from that, what we initially picked, right? That. Okay, so which means, this means absolute value of x is less than 1, right, from that. So so now that we have that, if that's the power series that represents, this is the power series that represents inverse tangent of x, then what we had was inverse tangent of x divided by x. So we can easily take this power series that we have, representing inverse tangent of x. Again, I missed my highlighter today because I forgot to bring it. This is representing this. So if we divide the left side, this by x, and all of this power series by x, we will end up with a power series that represents the inside of this integral. Okay, so let me write that down. Thus, if inverse tangent of x equals then that over that. And we're doing this because that's our integrand. That can be obtained easily by dividing, I hope I can fit all of that here, all of this divided by x. Like that, and of course divided by x. Okay, so let's simplify that. So we have on the left, we have just that, tangent, inverse tangent of x divided by x. On the right, so we have this divided by that is just a complex fraction. So we have divided by 2n plus 1. Change that to multiplication. So we, instead of divided by x, we end up with multiplied by 1 over x. Okay. Since x gets multiplied by the denominator, and then we can bring it up, which would be, with respect to the numerator, it would be x to 1 over x, or x to minus 1 power. It depends on how you prefer to simplify this, but the final answer will be the same. You could have written, we could have said, instead of this over x, we could have said all of this times x to minus 1 power. Okay, so after simplifying, so then we have, I guess we don't need that anymore. So we have so this x to minus 1 power will cancel this. We end up with just x to the 2n power. and then divided by, of course, 2n plus 1. Okay, so now that we have this, well, maybe I should bring this back. We have a power series representation for the integrand. So if we integrate that, we get a power series representation for the entire integral. Okay, so let's do that. Integral of inverse tangent of x divided by x dx. Of course, this is an indefinite integral, so we're going to get a c constant term plus, let's integrate this power series. The constants stay as they are, and then we get x to 2n plus 1 power divided by 2n plus 1 times 2n plus 1 power, right? So we get that divided by 2n plus 1, which is that, times again, since we're dividing by this new power, times again 2n plus 1 power, 2n plus 1. So obviously we can simplify this. We can just say 2n plus 1 squared. So let's do that. And we have c plus and so we have x to 2n plus 1 power divided by 2n plus 1 squared. Okay, so this is the power representation, power series representation of the integral we started with. And of course, the radius of convergence goes back to this absolute value of minus x squared. Okay, which would be, well, absolute value of minus x squared less than 1, which will reduce to r equals 1. Okay, so let me just add a note about that. Because r equals 1 for the series that represents, this is just, it's all about the theorem that we had, that the radius of convergence does not change throughout this procedure. So represents inverse tangent of x so r is still, radius of convergence is still equal to 1 for the series that represents inverse tangent of x over x. And by the theorem, my ink is running out. That also has r equals 1. Like that. Okay, I hope this discussion was helpful to your understanding of the material in this section. feel free to go over these examples, download my lecture notes. Of course, as I promised you, I will clean them up, and you can download them and then go over those same examples without looking at the solutions. Repeat that again and again until you feel comfortable with how to represent functions using power series. So, and I thank you for watching this video until the end. For now, have a nice day, and I'll see you again next time.